Welcome everyone to this mega talk. My name is Josué Tonelli-Cueto, and I will be presenting to you the talk, A Numerical Algorithm for Zero Counting for an Adaptive Speedup. Let's start with the internal story of the problem. So we have a real homogeneous polynomial system with variables x0, x1, x2, etc., where the first polynomial has degree d1, the second polynomial degree d2, etc. And we want, given this real homogeneous polynomial system, to be able to compute the number of projective zeros of the system. And for this, we want an algorithm that is deterministic, numerically stable, and that it has a good probabilistic runtime when we randomize the input. Note that this last condition, when we randomize the input, is necessary because as this algorithm will be a numerical algorithm, we can expect that the runtime will be depending on the input through the condition number. So in order to get a uniform bound of the runtime, it will be needed to randomize the input. So this algorithm was found by Cucker, Krick, Malajovich and Wschebor in their original trilogy, a numerical algorithm for zero counting. And on the first one, they proposed the algorithm and they did a condition-based complexity analysis of the runtime of the algorithm and of the precision of the algorithm. Then on the second one, they developed a condition number theorem, which allowed them, using integral geometry, to obtain a probabilistic analysis of the algorithm. And finally, they redid the probabilistic analysis of the condition number without using integral geometry. The important thing of these three papers is that they form the first milestone of the grid method that later on has been used by Cucker, Krick, and Suk for the computation of the homology groups of real projective algebraic sets, by Burgiser, Cucker, and Lerev for the computation of the homology groups of basic semi-algebraic sets, and by Burgiser, Cucker, and myself for the computation of the homology groups of general semi-algebraic sets, all of this in a numerically stable way. So this algorithm has essentially the three properties that we want. It's deterministic, is numerically stable, and has a good probabilistic runtime. Let's be a little bit more precise. This means that with high probability, I will not enter here on the technicism with how much high probability, the runtime of the algorithm on a random Gaussian super-small polynomial system is bounded by the maximum degree of the system to the number of variables squared times a constant. And this random estimate is both in the average and a smoothed case. So the important thing to remember about the Gaussian super-small ensemble, in the sense that I will be using, is that not all the polynomials must have the same degree. For those unfamiliar with this class of random polynomial systems, we only have to think of them as a class of Gaussian random polynomial systems, such that it is invariant under orthogonal transformations of the variables. Following the original trilogy, we have a couple of spin-offs by Ergür, Paouris and Rojas. In the first one, they gave the first non-Gaussian average complexity analysis in numerical algebraic geometry. And in the second one, they give the first non-Gaussian smoothed analysis in numerical algebraic geometry. Plus, they extended some of the results to certain classes of structure polynomial systems. But the important thing of these two papers is that they provide us with a robust probabilistic toolbox for analyzing numerical algorithms based on the grid method. And incorporating the spin-offs to the original trilogy, we can say that the CCMW algorithm performs well not only for the KSS polynomial systems, but for a wider class of random systems. More details about this will come later. So now here the question is, okay, we are speaking about high probability. But if you look many of these results in numerical algebraic geometry regarding the complex case, you will see that usually we have a bound on the expected runtime of the algorithm, not only on the probability that the runtime is big. So a natural question to ask here, let a random polynomial system as before, for example, a KSS, or fixing ideas, and we might ask ourselves, is the expected runtime of this algorithm finite? And unfortunately, the algorithm proposed by Cucker, Krick, Malajovich and Wschebor has not finite expected runtime, neither in the average case nor in the smoothed case. So here is an idea which goes back to my work with Cucker and Ergür on the Plantinga vector algorithm, is that if we do the algorithm by Cucker, Krick, Malajovich and Wschebor adaptive, then the complexity should depend on a kind of integral of the local condition on the sphere instead of on the maximum of the local condition on the sphere. And it happens that this expectation of the n power of the local condition number, it has finite expectation. So one idea is, okay, we do the algorithm adaptive, then we will get a condition base bound that depends on the integral of the condition of the local condition number on the sphere. And since this has a finite expected runtime, we are good and we have obtained an algorithm for our problem that has finite expected runtime. Unfortunately, the naive adaptive version fails. So this was done by Ergür and Han. And there one can see that if one is not careful at the moment of constructing an adaptive version of this algorithm, one fails. And the reason for this is that the bound will not be of the integral over the sphere of the local condition number to the n, but it will be to the 2n. And this 2 in the exponent is sufficient to get an infinite expected runtime. So what goes wrong, as we have seen, is this square in the exponent, which is produced by the criterion to select zeros in the algorithm. So now we will go to the algorithm and we will look what is inside the box. So the CCMW algorithm. So the algorithm starts by refining the grid until the Hausdorff distance between the grid and the sphere is small. We exclude points where the evaluation of the system is big, and we keep the points where the evaluation of the system is small. And then we post-process the selected points in order to get the correct count of points, because of course we can have several approximations for one zero. So now let's make this a little bit more concrete. So let's call delta the Hausdorff distance between the grid and the sphere. So we want this to be smaller than 1 over kappa squared, where kappa is the global condition number. You can see a definition in below the slide for those that are unfamiliar with this condition number. The only important thing that you have to keep in mind is that this number measures the numerical sensitivity of the real polynomial system with respect possible perturbations of its coefficients. And then we reject the points where this number is bigger than square root of the delta. And we keep the points where the valuation is less than 1 over kappa squared plus some normalizing constants. So there we can see that in the inclusion criterion, there is a square. And unfortunately, when we do the naive version of the adaptive CCMW algorithm, we get a square. Note that here, the Hausdorff distance, of course, since its ball has a different size, we use incorporate inside the grid. But now our grid will be composed by points and certain radius. So in order to keep track of how big are the radius, we want that this covers the sphere, and we want in a certain way that the radius are not too big, so are controlled in a certain way by the inverse of the local condition number. So if at a certain part the local condition number is very big, then we will have to take smaller balls around that region. And if the local condition number is smaller in another part of the sphere, then we can take bigger balls in that part of the sphere. And in this way, we will exclude the points that are essentially where the valuation is big, and we will keep the points where the valuation is small. Unfortunately, yeah, again, the square appears. And why is this? Why we get this square? I mean, this is the question. So let's recall Smale's alpha criterion. So in the Smale's alpha criterion, we have alpha, beta, gamma. Alpha is equal to beta times gamma. Beta is equal to the norm of the inverse of the tangent map times the valuation of fx. You should think of beta as the length of the Newton step. And gamma, you should think of it as some kind of regularity of the function at a given point. So essentially what the Smale's alpha criterion says is that if alpha is small, then around this point, there are no other zeros of the system, and then the Newton's method starting at this point will converge quadratically. In other words, at its steps, we will double the number of decimal places that we have. So this is a very good approximation of a zero. Okay, so we have this, and what is here we can see that okay, this beta and this gamma, maybe they are terms that we want to estimate in a certain way. So let's assume that the valuation is small in a certain sense. And then we have the higher derivative estimate, which says, okay, then you can control gamma by the local condition number. Okay, so then I don't need to compute all the higher derivatives that appear there on gamma. I only need to compute the local condition number, which is cheap to compute. And then we usually, a bad bound for beta is used. We bound beta by the product of the local condition number and the evaluation of the system at the point. And here is where the square comes from. Whenever you do this with beta, there is no way of getting around getting a kappa square, because you will get a kappa coming from beta and a kappa coming from gamma, and this will give you a kappa square. So the idea is pretty simple. Let's use beta directly. I mean, beta is used the same as computing one Newton step and seeing how long was that Newton step at the point. So this is what we will be doing. And for that, we develop a certain converse of the Smale's alpha theorem, which essentially tells us that if a point is sufficiently near the zero set, in terms of the regularity of the system around that point. So this is gamma. Then we can guarantee that the alpha is small. In other words, if X is sufficiently near the zero set, then the alpha criterion is satisfied. So this is why this is a certain converse of the alpha theorem. So in this way, we get a corollary that if the valuation of the system is sufficiently small, either the alpha criterion is satisfied, or either I don't have a root in the size of the balls that I'm taking around my points. So we can essentially, by the violation of the Smale's alpha criterion, we can exclude those points. Be sure that those points are excluded. So in this way, we can fix the algorithm. Note that the main change is that now we have beta fx instead of the evaluation of the system, and now we only have 1 over kappa. And this is essentially the thing that allows that we only get the integral of kappa fx to the n, which have a finite expectation. So here we add some extra tricks, and then one has to do a lot of things. So instead of using this condition number, we will be using this more different condition number. Note that there is a change in the norm and certain change in the normalization that we are doing. This change in normalization is used to guarantee that first, this second version of the condition number will have better Lipschitz properties. And then in many estimates, this will change the maximum of the degrees by its geometric mean, which is something that in a certain way is preferable. And on the other hand, we will also have some row normalization, which also have improves in certain degree the complexity of the algorithm. Of course, when we do all these, here I have also to comment that we will not be using Smale's alpha theorem. We will be using a version which I call delta theorem, which uses directly the condition number without passing through gamma. This also is because it gives better bounds. So now that we have seen, okay, there are a lot of technicism under the carpet, we put them there, and let's pass to state the main result and its technicalities. So let's pause a little bit with the probabilistic model for people that is not familiar with the probabilistic model. So we will consider Dobro random systems. So these are systems where we write each polynomial as fi equal as the sum, and note that we have this weird scaling in the coefficients given by the square root of the binomial of the multinomial coefficient that depends on the degree of the polynomial and the monomial term where it lies. This scaling is the same as that we have in the Koszlan-Sup-Smale model, and is there to guarantee, in the Koszlan-Sup-Smale model, is there to guarantee the orthogonal invariance. Here is to guarantee that things work properly when we do the probabilistic analysis. So what we want that this Ci alpha is that they are independent, that they are centered, that is, their expectation is 0, that they are sub-Gaussian. So this means precisely that when we take the expectation of the higher powers, this is bounded by some constant times L to the L half, and that we have some anti-concentration. So in other words, that the probability that the coefficient is near any point is small. This last property of anti-concentration is equivalent to having an absolute continuous density bounded by rho I. And when we have all these properties in the coefficients with this scaling, we are in front of a Dobro random system. We can do a variation to get a smoothed version of this. So in our probabilistic model, we can also consider a smoothed version. And yeah, let's recall that when the Ci alpha are normal random variables of variance 1, then we recover the usual Kosland-Supes-Smale model. So now we have the language to express the main theorem of the paper, which is there is a deterministic numerically stable algorithm, which I call ACKMW, that is adaptive Cucker, Krick, Malajovich and Wschebor, that given a real homogeneous polynomial system computes the number of projective zeros. And this system just satisfies that the expected runtime is bounded by one summand that is essentially maximum degree to the n times capital N, and then another summand where we have the Bezout bound appearing. The first summand is a consequence of working with the infinity norm. So this is the summand that comes from the computation of the infinity norms. And the second summand comes from the actual computation that we are making. And this bound holds for Dobro random polynomial systems. And here I'm omitting the relevant constants, technical constants that we will need to add for this bound being valid for all Dobro random polynomial systems. So, and this we can consider that this is a good probabilistic runtime compared with other algorithms for computing all the real projective zeros. Is a good bound. And moreover, here it is not written, but this algorithm does not only count the zeros, but we can also use it to produce approximations of all the real projective zeros. And another extra property that it has that I think is nice is that this algorithm is parallelizable. So we can run it in parallel, accelerating it a lot. So, okay. We have this result, so now let's finally discuss the final work, future work. And the future work, I will focus on one project that is the motivation for this, that is the homology computation of semi-algebraic sets. Because as a consequence of the algorithm of Cucker, Krick, Malajovich and Wschebor not working in finite expected time means that these other algorithms that I mentioned before for computing homology don't work in finite expected time. Therefore, the fact that now we have a version that runs in finite expected runtime ponders us to questions, okay, can we make these other algorithms run in finite expected runtime? Because this was something that was thought to be out of reach, and now, okay, it is nearer. Unfortunately, okay, it seems that there is work to do. On the one hand, the positive news, we are able to produce correct adaptive samples, at least until this a basic semi-algebraic case. Unfortunately, we need to improve the post-processing of these adaptive samples, because if we do the analysis and the methods as we do, essentially the expected runtime that we get at the end will be infinite. So we can get the sample in finite expected runtime, but then we will want to process the sample in order to get the homology, then we will jump to infinite expected runtime. So there is work to do there. So thank you very much for your attention to Syntac, and I hope that you have enjoyed this talk. And for any question, don't hesitate to contact me either during the conference or afterwards through email or other electronic means.